8b, hypothesis testing for population means, where we have a large sample or the population standard deviation is known. Method 2. Right? Previously we talked about using p-values to perform a hypothesis test for a population mean with a large sample of the population standard deviation being known. Now we're going to deal with rejection regions. Now personally, rejection regions is my preferred method of doing hypothesis testing, mainly because it works no matter what distribution we're working with, whereas you'll see that p-values only really work when you're dealing with a normal distribution, so when we're able to use the z distribution. Whereas you saw in our introduction that if we're dealing with a claim about a population mean where we have a small sample and the population standard deviation is unknown, we'd have to use the t-distribution table. And that does not work for p-values. If we were doing it for a population standard deviation or variance, we would have to use the chi-square distribution table, and that does not work for p-values either. So I like using rejection regions because it works for all distributions. So what do we mean by rejection region? Well, basically with a rejection region, we're changing the process slightly. Previously, when we had a p-value, we took our test statistic, x bar, and we worked it to the point where we calculated the z-score, and then from the z-score, we found a p-value. So we went to the table and ended up getting a p-value, which we then compared to the significance level alpha. The difference with dealing with rejection regions, we're still going to start with the test statistic and take it to our standard score, z-score or t-score or chi-square score, whichever it is. But we're going to stop there rather than finding a p-value, rather than taking that down into the table. So we just have to calculate z or t or chi-square, depending on which we're working with. So in this case, we're going to find z. And what we're going to do is we're going to take alpha and we're going to turn that into a z-score by doing a reverse table lookup, z sub 0. And then we're going to compare our z-score that we calculated to our z sub 0, our critical value. If you remember, with confidence intervals, we had critical value z sub c. Now we have z sub 0, which essentially means the same thing. It's our critical value. And we're going to compare that to our z-score. But even better than just comparing it to our z-score, we're going to have our distribution, and let's say it's a right-tailed test. We're going to put z sub 0, our critical value, as a boundary, and we're going to take the z-score that we calculate and place it in the distribution. If that z-score ends up in the tail, that tail is known as the rejection region. So if that z-score ends up in the rejection region, that tail, then we reject the null hypothesis. If that z-score ends up outside of the rejection region in the rest of the distribution, then we fail to reject the null hypothesis. So we have this region that's created from this critical value z sub 0, and we just put our z-score wherever it fits in the distribution. If it's in that tail of the rejection region, we reject the null hypothesis. If it's not in that tail or rejection region, we fail to reject the null hypothesis. And then from there, we go and do the exact same things that we did with our p-values. So we do the same thing of saying, okay, at a such and such significance level, there is or is not sufficient evidence to reject or support the claim. We can make our final statement about that claim. So that's our process. So this is where we need to be able to do that reverse table lookup again. And remember with confidence intervals, I first started with us and I had us look it up backwards before I told you about that little table in the bottom left-hand corner. Well, here we have to look that up specifically backwards because it depends on whether we're right-tailed, left-tailed, or two-tailed, exactly how we get that critical value z sub 0, or where it's located. So we can't just use that table in the bottom left-hand corner anymore. So let's revisit the Jelly Belly example. Remember with the Jelly Belly example, and I'm just grabbing it so I have the correct wording of what happened. Jelly Belly claims that on average you get more than 16 ounces of jelly beans in every 1 pound bag. So their claim, I always label the claim specifically as that because remember at the end we need to know whether the claim was the null hypothesis or the alternative hypothesis. So it just makes my life easier. Was that you get more than 16 ounces, mu greater than 16. 40 bags are randomly selected and weighed with a sample mean of 16.4 ounces and a standard deviation of 1.2 ounces. Make a statement about the claim at a 0.02 significance level. So that's what we had from that question. And then we come in, we can start pulling information. Well, mu is greater than 16, that's the alternative hypothesis. Therefore, the null hypothesis is less than or equal to, because that's the complement of it. Remember, the null hypothesis always includes equality. The alternative hypothesis never includes equality. So less than that H sub O is that mu is less than or equal to 16. The alternative hypothesis points the way, telling us what type of test, so we're going to deal with a right-tailed test. Which means we've got something that looks like this. Okay? Since we're dealing with rejection regions, alpha is going to be the area in that tail. And that's going to give us z sub 0, and alpha is 0.02. So that's the area in that right-hand tail. Remember that with a z distribution, the table always gives us the area to the left. So that means the area to the left of that is 0.9800. If we go to look this up in the table, we do a reverse table lookup, and we're looking for the closest thing we can find to 0.9800. So I look in the body of the table, and the closest thing I find to 0.9800 is 0.9798. So I came out with 0.9798, which gives me a z-score of, if I find it again, 9798, a z-score of 2.05. So 2.05 will be our critical value. Z sub 0, 2.05. So we looked up, we found the closest thing we could to this in the body of the table and looked at what z-score that gave us, so it gave us 2.05. That's our critical value, z sub 0. So now I need to find my z-score, and remember we did that by taking x bar, 16.4, and subtracting our mean of 16, or our claim of 16, and then dividing by our standard deviation, 1.2, over the square root of 40. And z came out equal to, I believe, 2.11. But let me just plug that in to make sure I'm not misstating that. In fact, it was still in my calculator, so 2.11. So z is equal to 2.11. Now we look at this distribution and say, in this distribution, where is a z-score of 2.11? Well, if that's 2.05, remember this here, that's 0, right? The 0 is in the center. So 2.11 is going to be in that tail. And if it's in that tail is known as the rejection region. So that tells us that we will reject the null hypothesis. So we reject the null hypothesis, which means we're ready to make our final statement. At a 0.02 significance level, we rejected the null hypothesis, so there is sufficient evidence. The claim was the alternative hypothesis, so to support the claim. So notice that our method did not really change much. We still found which determined whether the claim was the alternative hypothesis or the null hypothesis. We found the other hypothesis, the complement of it. We used the alternative hypothesis to determine what type of test. We found our z-score by calculating it the same way we did in the past. The difference was, instead of taking the z-score and looking it up in the table to get an area and dealing with that, we took our significance level and said, okay, what is that? And found a z-score associated with that by doing a reverse table lookup. Then we were able to just take this value and plug it in to find the spot, and if it was in the tail, we rejected the null hypothesis. If it wasn't in the tail, then we failed to reject the null hypothesis. Now, I'm going to do the same thing with this that I did when we were dealing with p-values, because it works well to show what's happening with it. Let's modify this slightly. So I'm going to get rid of that. And get rid of that and that. All that information there. I'm going to get rid of that and that, and I'm going to change it to Jelly Belly claims that on average there are 16 ounces of jelly beans in a 1 pound bag. So they're claiming that mu is equal to 16. Includes equality, that is the null hypothesis. So the alternative hypothesis is that mu is not equal to 16. If the alternative hypothesis is not equal to, it splits it into two pieces, so it is two-tailed. So we have two tails here. We have z sub 0 and negative z sub 0, so we have two critical values. Alpha is equal to 0.02, that's the area in the tails combined. So half of 0.02 is 0.01, so we have 0.01 in that tail and 0.01 in that tail. I'm going to put my additional two zeros in here to remind me that we're going to do a reverse table lookup in here. So now I'm going to grab my table and say, and this worked out nicely, this is the area in that lower tail. Look at the body of the tail for the closest thing we can to 0, 1, 0, 0. So that's on the negative side, 0.0100. I come out with 0.0099. 0.0099. So that's just one off. And that is negative 2.33. So negative 2.33. And then if that's negative z sub 0, then positive z sub 0 is just positive 2.33. So we have our critical values creating our rejection regions. Now we have two rejection regions. And now we look at the z-score that we already calculated. It still calculates the same because I didn't change any numbers. So we still have this. So we have a z-score of 2.11 from our test statistic of 16.4. And where does that fit into this distribution? Well, if this is 0 here, 2.11 is less than 2.33, so it's in the center, right? It's not in a tail, so it's not in a rejection region, so we fail to reject the null hypothesis. It's not in a rejection region, so we fail to reject the null hypothesis, which means we're now ready to make our statement about the claim. Start with the significance level. At a 0.02 significance level, we failed to reject the null hypothesis, so there is not sufficient evidence. The claim was the null hypothesis to reject the claim. So at a 0.02 significance level, there is not sufficient evidence to reject the claim. And that's how we can find, or how we can test claims about the population mean using rejection regions. And you'll see for the rest of the hypothesis testing that we do, that we will use rejection regions.